Okay, we'll go ahead and get started. Can everyone hear me and can you see my computer screen okay?
Yes.
Thank you. So what we'll do today is we'll go ahead and review the answers for quiz 2, the quiz you took last week, and then we'll continue on with chapter 14. That's the kinetics chapter. Then Thursday of this week, we'll finish up chapter 14. And then next Tuesday, so a week from today, we'll have an exam on covering chapters 13 and 14. Okay, so quiz number 2, the first question was the phrase like dissolves like refers to the fact that, and the answer was B, polar solvents dissolve polar solutes and nonpolar solvents dissolve nonpolar solutes. Number 2, when solutions of strong electrolytes and water are formed, the ions are surrounded by water molecules. These interactions are described as a case of, and the answer there is hydration. Number 3, an unsaturated solution is one that the answer was has a concentration lower than the solubility limit. So if it's saturated, it's reached the solubility limit. If it's less than that solubility limit, it's unsaturated. And if it's more than the solubility limit, then we call that supersaturated. Number 4, which one of the following is most soluble in water? The answer was CH3OH, that's methanol. The reason for that is it has the least amount of nonpolar functionality to it. So when we look at the different choices that we had, the more of those CH2, CH3 groups it has, those are nonpolar. And since methanol has the fewest, it's the most soluble in water. That goes back to the like dissolves like thing from question 1. Number 5, what's the concentration in parts per million of a solution which is prepared by dissolving 15 milligrams of sodium chloride in 200 mils of water? So a couple things you needed to take into account. One is if we are calculating parts per million, we want the analyte, the solute in grams, and then we want the total amount in grams. So 15 milligrams, we needed to convert that to grams. So I did that by remembering milligrams, 10 to the minus 3 grams. So 15 times 10 to the minus 3 grams of sodium chloride. Density of water is 1 gram per mil. And so the total weight for 200 mils is 200 grams. So now I have the answer set up in grams per gram, which is what I want. And so if it was percent, I'd multiply by 100. If it's part per billion, it would be times 10 to the 9th. The answer needed to be expressed in parts per million, and that's 10 to the 6th. So then I multiply that answer by 10 to the 6th and get a value of 75 parts per million. Number 6, as the concentration of a solute in a solution increases, the freezing point of the solution decreases and the vapor pressure of the solution decreases. So both of those properties, colligative properties, decrease as more stuff gets into the solution. Number 7, what's the concentration in molarity of HCl in a solution that's prepared by dissolving 25.5 grams of HCl in a 20-liter volumetric flask with water? So we know molarity is moles per liter. So we needed to go ahead and change the 25.5 grams of HCl into moles. In order to do that, I needed to calculate the molecular weight, and that's the 36.453 grams value. So I multiply 25.5 grams times 1 mole per 36.453 grams. So now my numerator is in moles, and then divide that by 20 liters, and then I get a value of 0.0350 molar. Number 8, we're told the concentration of urea in a solution prepared by dissolving 16 grams of urea in 39 grams is how many molal? That's the question. So we needed to remember that molality is moles of solute divided by kilograms of solvent. So in this case, the solute is urea, and we're told that urea's molecular weight is 60 grams per mole. So 16 times 1 mole divided by 60 grams, that gets the numerator into moles of urea. And then if we have 39 grams of water, we need to change that into kilograms. So we'd slide the decimal place over to the left 3 places, and that's 0.039 kilograms. And then if we do the math there, we get 6.8 molal. Number 9, what's the molarity of sodium chloride in solution that is 13% by mass sodium chloride and has a density of 1.10 grams per mil? So once again, if it's molarity, we know our final answer has to have moles in the numerator and liters in the denominator. We also hopefully remember that when we have something expressed in weight percent, which is what that 13.0 value is, we can do the problem by saying on a 100-gram basis, we have 13 grams of sodium chloride and 100 grams of solution. So if we set up that 13 grams in the numerator and use our molecular weight for sodium chloride, which we needed to calculate, and that value is 58.453. So that 13 grams times 1 mole per 58.453 grams, that gives us our numerator in moles of sodium chloride. Then in the denominator, we have 100 grams of solution. We need to get that changed into a volume measurement, in particular liters, since its molarity is our final answer. So we can use our density value of 1.10 grams per mil to convert the 100 grams into a volume, in this case milliliters, and then we can use 1,000 mils is equal to 1 liter to convert mils into liters. We do all those calculations and we get a value of 2.45 moles per liter. Then the final question, number 10, we have a mixture that contains 41 grams of a non-electrolyte and 160 grams of water. And we're told the freezing point is now minus 1.34 degrees. So normally the water's freezing point is 0. We have that unknown non-electrolyte in, it's dropped the temperature by 1.34 degrees. We're told our constant for this is 1.86 degrees C per molal for water, and we want to know what's the molecular weight of the unknown solute. So we have our formula delta T sub F equals minus I K sub F times small, that's a small m, so that's molality, moles per kilogram of solvent. Remember, we said this is one of the times when we do need molality rather than molarity. So if we go ahead and plug in the information that we were given in the problem, we have that temperature change minus 1.34. It's a non-electrolyte, because it's a non-electrolyte, our I value is 1. The Kf value we're told was 1.86, and then the unknown is the molality. So we go ahead and we solve for that molality value, and we get 0.720, but that's moles per kilogram of solvent. What we want to know is the molecular weight, which is grams per mole. So what we can do is we know the number of moles per kilogram of solvent is 0.720. So we can set up a relationship of moles of the unknown divided by 0.1600 kilograms of water. Because remember, in the problem, we were told that we had 160 grams of water. So we can substitute in that water expressed not as grams, but kilograms in our molal definition. And so now we can solve for moles of unknown. We go ahead and solve for moles of unknown, and then we go back and we say, we know how many moles, and we know from our problem that we had 41 grams of the unknown electrolyte. So we know that those number of moles, 0.1152, represent 41.0 grams. So if we're looking for molecular weight, that's grams per mole. So we take our 41.0 grams and divide it by 0.1152 moles, and we get a value of 356 grams per mole. So the other comment I'll make about this one is if you think of molecular weights of compounds, which is what this was asked for, and we look at the choices that we had 283, 356, 0.720, 4.74, 0.355. If you think about it a little bit, the 0.720 and the 0.355, we probably could rule those out just because if we think of molecular weights of compounds, what is that? Molecular weight is the sum of the atomic weights of all the atoms that make up that compound. And our smallest atomic weight is hydrogen of 1. So that tells us we have to have at least, it has to be 1 or greater. So those numbers that were less than 1, we could have ruled out based on that. 4.74, that's a pretty small number. It'd have to be a pretty small molecule to have a molecular weight of that. So we could sort of rule that one out too. And that left us with 283 and 356. So I guess my point here is if you didn't know how to do this problem and you were going to guess, you should have guessed between 283 or 356. So you kind of had a 50-50 chance on that. So any questions about anything on the quiz? Okay, let me go ahead and pull up chapter 14 then, and we'll start on that. So last week, this is where we kind of left off, where we were talking about reaction rates and things like that. And we had this plot of where we showed that reaction rates in general tend to slow down with time. And there's some various reasons for that. A big one is that there just isn't as much material around, and reactions are dependent upon the concentration. So let's kind of move on and talk a little bit more about rates. So we can follow rates using either the reactant or the product, but does it give you the same rate depending upon which one you're looking at? And the answer to that is maybe. It kind of depends. And so let's take a look at what we mean by that. So the rate's dependent on stoichiometry. And so if we use that butyl chloride example, and so just to go back to remind everyone what that equation was, it's this equation up here where butyl chloride reacts with water to form butanol and hydrochloric acid. So we're still talking about that reaction. So based on that, we know that as the butyl chloride goes down, so that's this delta butyl chloride molarity divided by delta T. So as butyl chloride decreases with time, we have an increase in the butanol with time. Because of that, the rate for the butyl chloride will be negative since that's going down in concentration, and the rate of the butanol is positive because that's what's being formed. So in that case, our reaction stoichiometry was 1 to 1. So in other words, we knew that for every mole of butyl chloride that was being used up, 1 mole of the butanol was being formed. So what if it's not a 1 to 1? So let's take a look at this general equation here of A plus B equals C plus D. And then the lowercase letters on this equation are meant to represent the stoichiometry of the equation. And so the way you would express the rate in that case is you'd still have your delta, the constant molarity divided by delta T. That stays the same, but now you have 1 over whatever that coefficient is in front of it, multiplying in front of it. So if A was 2 here, the small a was 2, then that would be 1 over 2 times the change in concentration of A divided by the change in time. And once again, the reactants have the minus sign because they're going down. The products have a positive sign because they're what being formed, their concentrations are going up. So what we see there is if it's not a 1 to 1 reaction stoichiometry, then it's 1 over whatever that coefficient is in front. So down at the bottom, we have an example of where O3 converts to O2, and we have 2 moles of the O3 going to 3 moles of O2. And so we see that rate would be expressed as minus 1 over 2 times the change in O3 molarity divided by a change in time, and divided equals 1 over 3 because of that 3 being the coefficient in front of the O2 times the change in O2 concentration divided by delta T. So once again, we have the negative sign for the reactants, positive sign for the products, and we see that based on the reaction stoichiometry, it's 1 over whatever that coefficient is. And that allows us to express the rate. So we've said before that concentration affects the rate. So how do we determine what that effect of the concentration is on the rate of the reaction? And so we have our reactants. If we increase or decrease the concentration, what do we do to determine the rate? Well, the only way to figure this out is to do experiments. And what you do is, let's say you have 2 reactants. What you do is you keep one of the reactants constant and then vary the concentration of the other reactant and do those experiments and see what values you get. And then that helps you determine what the rate how the rate is affected by the concentration. So you'd hold one of the reactants constant, vary the second one, do a series of experiments like that, collect that data, and then you would do vice versa. You would take the second one that you had been varying and hold that constant and vary the one that had been held constant and see what that effect is there. The reason why you have to do both of them is you could have instances where the two concentrations have a different effect. And so you want to determine what that is if it is different experimentally. So here's just an example of how that type of experimentation would play out. So in this case, we're reacting ammonium ion, NH4, plus nitrate, NO2. And so in experiments 1 through 3, you can see that in each experiment, the NH4 plus concentration is doubled. So it's the first experiment at 0.01 molar, the second 0.02 molar. So that's twice the first one. Then the third one is twice the second one, 0.04 molar. The NO2 minus concentration has been held constant in this case at 0.2 molar. What we see over here at the initial rate, remember we talked about how from that plot we can calculate what the initial rate is. So from the initial rate data, we see it goes from 5.4 to 10.8 times 21.5. All of those are 10 to the minus 7th molar per second, per second. And so what that tells us is it's a decrease, or rather an increase of 2x with each of those. So we see that doubling the NH4 plus concentration results in doubling the rate. Then the next thing you would do is to go ahead and keep the ammonium ions constant. So in this case, they're all 0.2, and then change the nitrite ions. So the nitrite goes from 0.02 to 0.04 to 0.08. Once again, each one is doubling. And what we see on the right-hand side of those rates is we see that the rate doubles in each instance as we double the concentrations of the nitrite ion. So when we go ahead and look at this to figure out the order, if we go ahead and ratio rate 2 to rate 1, so in other words, if we say take the ratio of the second experiment rather, and divide it by the rate of the first experiment, and do the same thing to the concentrations, we see that to make the math work, it has to be 2 equals 2 to the x. So 2 to the x, if x is 1, then 2 equals 2. So if that rate had gone up 4x by a factor of 4, so then we'd have 4 equals 2 to the x, and in that case, x would be 2, so the order would have been 2. But this tells us that the order for the ammonium ion is 1. So basically the rate doubles with a doubling of the concentration, the order is 1. We can kind of do this same thing with the nitrite ion by looking at how the rates change as the concentration changed. We said that the same thing is happening when we kept the ammonium ion constant and doubled the NO2 minus concentration. We saw that doubling. So if we do this same ratioing, we see that the order for that is 1 as well. So if we were to write the rate law showing this relationship, we have that down here at the bottom. We have that rate equals the rate constant times the ammonium ion concentration, and it's implied that that's a 1 as the exponent on it. And then the nitrite concentration And once again, we determined that was 1. And so there's an implied 1 there for that reactant. So that exponent tells us the reaction order with respect to each reactant. So first order for NH4 plus, first order for NO2 minus. The reaction overall is second order because we have 2 reactants here that impact the rate of the reaction. And so we have 1 from the NH4 plus, we have 1 from the NO2 minus, so 1 and 1 is 2. So that overall reaction order is a value of 2. As we'll see in a little bit, sometimes these reactions, just because you have reactants doesn't mean they impact the rate of the reaction. That may sound a little odd, but it's true. And so that's why in this case, both of these, the concentration of both of these impacted the reaction rate. Sometimes you have it where that's not the case. And so then if the NH4 plus or the NO2 minus didn't change that reaction rate when we varied the concentration, then it wouldn't show up in this rate equation. And so sometimes you get things that are reaction order of 1 for the whole reaction, not just 2 or above. So K that we're talking about is the rate constant. And rate constant tells us how the reaction goes. And as you've seen a little bit when we talk about reaction mechanisms, it's really kind of telling us what the slowest part of the reaction is. The key about rate constants are that, normally when we think of constants, we think that they don't change. Rate constants are temperature dependent. So whenever rate constants are given, there should be a temperature associated with it, because as you change that temperature, the rate constant will change. So before, when we were talking about rate, we talked about stoichiometry playing a factor in there. When we talk about order, it really doesn't have anything to do with the stoichiometry of the balanced equation. So sometimes it does, sometimes it doesn't, but really the only way to figure out the order is by doing the type of experiment I just described. And so that's by doing that experiment where you keep everything, all reactants except 1 constant, and then varying that concentration and seeing what happens to the rate of the reaction, and then going back and doing that type of thing for all the reactants. So here we have some examples of 2N2O5, and we see going to NO2 plus O2, and we see there that the rate is the rate constant times the concentration of N2O5. So even though N2O5 has that 2 in front of it for the stoichiometry of the balanced equation, what we see is that it's not a second order reactant. It's a first order reactant. Then on the other hand, we have H2 plus I2 going to 2HI. And in that case, the H2 and the I2 with coefficients of 1 for each, those both are first order reactants. So that one matches. So the first one didn't match, the second one did match. We look at the third one, CHCO3 plus Cl2, and we see there that they don't match there as well. We have rate order of 1 for the CHCO3, but for the Cl2, it's 1/2. So this is just an example to highlight that order does not equal stoichiometry. And so you got to get to that order, those order values, by doing experiments. Any questions about anything so far? Okay. So when we think of the rate constant, there's kind of a rule of thumb that if the rate constant is 10 to the ninth or higher, the reaction is considered fast. If it's lower than 10 to the ninth, then it's considered slow. So just a rule of thumb when you're looking at reaction rate constants to know if that reaction is slow or fast. One reason those rate constants of having kind of this rule of thumb is good to know is if you do have a slow reaction, then you may want to think about what can I do to speed up the reaction to kind of make it faster. And remember I said earlier that temperature does change this rate constant. And so that's a case of where if you have a slow reaction, you could possibly increase the temperature of the reaction to speed it up. We'll talk about something called a catalyst a little bit later. That's another thing you can do to speed up a slow reaction. So we're going to talk a little bit about the order of reactions. So first order, second order, things like that, reactions. And so for a first order reaction, then that would be a case of where we would have the rate law being expressed as the rate equals the rate constant times the concentration of one of the reactants, and that reactants would just be the concentration. So what that means is that the reaction only depends on one of the reactants in the reaction in terms of how fast it goes. And so in this case, they show us methyl isonitrile going to acetonitrile, and really the only thing that matters is the concentration of that methyl isonitrile. And so it's not uncommon to have first order reactions. There's a lot of times where there's one key reactant in the reaction. Even if you have more than one reactant, you have one key reactant, and really that concentration is the one that drives the rate of the reaction. So when we have a situation like this, where the rate is equal to simply the rate constant times the concentration of one of the reactants, that's considered a first order reaction. So in this case, it would be first order with respect to the reaction and first order with respect to the concentration of A. So we're going to go through just some rearrangement of formulas to get to how we can express these. And one of the things, so I wouldn't worry so much about the process of how we get to the final formula. The final formula is what we're most interested in. But the other thing I want to point out is that you'll see some plots in a little bit of these reactions. And that's probably one of the easier ways experimentally to determine if something is first order or second order or whatever the order of the reaction is you'll see that to get a linear plot, you plot different things depending upon what the order of the reaction. And that's probably the most common way that I'm familiar of determining the order of the reaction experimentally, is to do those plots and see what plot gives you linearity. So let's just go through this quickly so you kind of see how we get to some of these final equations. And those would be the final equations that you would use in calculation. So for first order, we said that rate equals the rate constant times the concentration of A, the molarity of A. We also know that we can write rate as minus, because we're using up the reactants, the change in A, so in other words, the change in that concentration over a change in time. So we know those two relationships we've seen already. So now what we can do is, if both of those are equal to rate, we can say those two are equal to each other. So now we say that rate constant times the concentration of A equals minus the delta A divided by delta T. And that's our differential rate, what's called a differential rate law. We can rearrange this. So in other words, we're just taking the delta T and multiplying that to both sides. And so now we have K times minus K times delta T, and then we divide each side by the concentration of A. So it's delta A over A equals minus K delta T. We can do some mathematical things to this, and basically we develop the integrated rate law. And what that allows us to do is it allows us to relate the initial concentration to the concentration at time t. And this is the formula that we're interested in. And so by doing this natural log, we can then say natural log, and make sure on your calculators you know which is the natural log key. It's not the base 10 log. So the base 10 log is usually log on your computer or your calculator, and the natural log is ln on your calculator or your computer. So natural log times the concentration at some time divided by the concentration at time 0, so the initial concentration. So basically for this, you would need to have the concentration of the analyte that you started with the reactant that you started with, and then maybe 60 seconds later, you have the concentration of that same analyte, and that would be the T, and then you would have K, which is the constant that we talked about, the rate constant, and then you would have the time that you're at. So the time would be that 60 seconds. You can further rearrange this. You can further rearrange this equation at the bottom to get it to be natural log of A at time t equals minus KT plus natural log of A at time 0. And if you look at you say, why would you want to rearrange that? Well, you want to rearrange this because if you look at it this way, now what you can see is if you think of the y equals mx plus b, that's the standard equation for a straight line. And y would be natural log of A at time t. M, which is the slope of the line, would be minus K, and then T would be the X variable. And then the natural log of A0, that's the y-intercept. So what we see here now is if we plot natural log of A versus time, we should get a linear plot, because this is what our rearranged equation is telling us, is that if we plot natural log of A at the different time points on the y-axis and the associated times for each of those on the x-axis, if we do that plot, then we should get a straight line. The slope of that line should be represented by minus K. Okay, minus K is the M in our line equation. And then natural log of A at time 0, that would be the y-intercept. So in other words, the y-intercept is when x is 0. So let's take a look at what that looks like. We'll see that in a moment here. Whoops, guess we got to wait a bit before we see that. Okay, so as I said, we can find that what that rate constant is by looking at the slope of the line. So if the slope of the line, this goes back to our y equals mx plus b. If our slope of the line is minus k, then we know we can find the rate constant k just by taking the opposite sign of that. So that's the reason why people would express it like this. Usually when you're using the formula to do a calculation, you use more of this presentation of it. Okay, this natural log of these ratio and equals minus kt. But because one easy way to find rate constants and to see the order of it, so in other words, if it's first order, it's going to be linear with natural log of a versus time. So by doing the plot, you're able to simply tell if it's a first order, and then if it is a first order, you're able to pretty easily figure out what the rate constant is. Okay, any questions about that? So we'll go through that again for some of the other order reactions, but it's kind of the same thinking of where you start with these base formulas, and then you do some mathematical manipulation and rearrangements to get it into more usable formats that allow you to then do some plotting, and from the plots, then you can pretty easily get some additional information that you might need. Okay, when we talk about reactions, you'll hear a term called half-life, and the half-life is defined as the amount of time it takes for 1/2 of the reactant to be used up. So if you start with 10 molar concentration, half-life would be the amount of time it would take to get to 5 molar concentration. So you could calculate that half-life. At any time during the reaction, you can recalculate out half-life. So for instance, in that example I just gave you, you start at 10 molar, you could calculate out the time it would take to get to 5 molar, to get to that half-life. Well, now you're at 5 molar, you could then calculate out how long it would take to get to 2.5 molar, and kind of on down the line. So once again, half-lives are used to kind of get a feel for how fast the reaction is going, and gives you a feel for how long it's going to take for the reaction to come to completion. So if we go back to our first order reaction equation that we talked about just now in the last slide, we have this natural log of A equals minus KT plus natural log of the initial concentration. We defined half-life as the amount of time it takes to get to half of the initial concentration. So by definition then, this natural log on the left concentration for A, we can substitute that concentration with the initial concentration, which is the A sub 0 divided by 2. Because if we're saying we're using up half the reactant, so that would be the initial reactant divided by 2. We can also change the time value in that formula. Since we're looking for the half-life, we're looking at 1/2, the time at 1/2. So we go ahead and make those substitutions, and then we start and we do some rearrangement of things. And by rearranging formulas, we get natural log minus the natural log of initial divided by 2 plus the natural log of initial equals K times T at half-life. we can go and further rearrange that. So in other words, we do our shifting over there, so we get our natural logs all together. Whoops. And now what we get is natural log of A0 divided by A0 divided by 2 over 2 equals KT 1/2. If we flip that A0 divided by 2 that's in the denominator over, we see that the A0s cancel out, and we're left with simply the natural log of 2 equals KT to the half. Natural log of 2 is where this 0.693 comes from. So if you do the natural log of 2 in your calculator or your computer, you should get a value of 0.693. So we have 0.693 divided by K. That gives us the half-life time. And so if you want to find out the half-life, and this is for a first-order reaction only, okay? For a first-order reaction only, you would have 0.693 divided by your rate constant, and that would tell you what that half-life time is. Once again, you know, I think it's good to see how these equations are derived and kind of see the process of going from the initial down to this final half-life. So certainly, you know, take a look at that and make sure you understand it. But really, the one you're going to use if you do any calculations, for instance, for a half-life calculation for a first-order equation, it's going to be this last equation that you're going to use, where the half-life time is equal to 0.693 divided by the rate constant. Okay, so let's look at second order reactions. So second order reactions mean that the rate depends on, it can be one reactant that is second order in just that reactant, but the second order reaction can also be two reactants, each first order. Remember, we talked about that earlier. So the example we're going to work through, I believe, is going to be just one reactant that's a second order for that reactant. But it doesn't have to be the reactant. Second order reactions can be either way. The example we're going to go through is where we have one reactant that is a individual reactant is second order, which makes the whole reaction second order. Okay, so in this example, we're going to kind of walk through this like we did for the first order reaction to kind of see how things play out. So we have a rate equation of rate constant times that reactant concentration squared. And then we also can say rate is equal to minus the change of A divided by the change of time. We do that rearrangement and setting these equal to each other like we did the last time. So now we have K A squared equals minus delta A over delta T. Shift things around once again, rearrange so we have our concentrations together, and then we have the K delta T. We do some calculus and we wind up with 1 over A equals 1 over A0 plus KT. So the key thing here is, if we look at this last equation, and it would be a little more clear if, I think if KT is written KT plus 1 over A0. But we get that same y equals mx plus b type of relationship. So in this case, the y equals 1 over A concentration. The mx, m once again is our rate constant K. The x is T, and then plus y would be 1 over A0. So this would be y equals mx plus b. So this b is 1 over A0, that's the y-intercept. Y is what we're plotting on the y-axis, and x is the t, the time, which we're plotting on the x-axis. So what we saw is, for first order, we had natural log of A versus T to get something that was linear. And for second order, it's 1 over A versus T. So in other words, 1 over A plotted versus T, we get that linear. We get that linear plot. And this is a real easy way to see if your reaction is first order or second order. Is you do this first order plot, natural log of A versus time. If it's linear, then you know you have first order. If you do that plot and it's not linear, then you know it's not first order. If you do 1 over A versus time, and that's linear, then you know you have a second order reaction. If it's not linear, then you don't have a second order reaction. So like I said, this being able to rearrange these relationships in a way that gives you what should be a linear plot is a real nice, straightforward way to see what order your reaction is, and also to figure out that rate constant. Because remember, we go back and we look at this slope, and from the slope of the line, if it is linear, we then get the rate constant off that information. So here's an example of where we have decomposition of NO2. So it goes to NO plus 1 over O2. And what we see is we have two plots here where someone went and did the experiment where they ran the reaction and sampled over time and got concentrations of NO2 and saw how it went down over the time course. And then a plot was done of 1 over NO2 versus time, and that's the plot on the lower right-hand side. This one here. And then they also did the plot of natural log of NO2 versus time. And remember, we said that if it's first order, if we plot natural log of whatever it is, the concentration versus time, it'll be linear. If it's second order, if we do 1 over the concentration then versus time, then it's linear there. So if you saw these two plots and you were asked, is it first order or second order, you would look at what was plotted, natural log in this case versus time, 1 over 1 over the concentration in this plot below. We see that one is linear. Okay, we'd go back here and say, okay, 1 over versus t is linear for a second order. So that would tell me this is a second order reaction for this based on these plots. And then if I calculated the line fit for this and then got the slope, then I could get the rate constant as well for that. Okay, we talked about for the first order reaction, we talked about how we could go ahead and do some rearranging and be able to calculate the time for half-life. And so we can do the same thing for second order reactions. So here's our formula. 1 over A equals 1 over A sub 0 plus KT. And then we start doing that arrangement. The first thing we do, similar to the last time, is we say, if we're talking half-life, then this concentration A on the left-hand side is really A sub 0 divided by 2. And our time is the half-life time. So we go ahead and do that. We start doing the rearrangements. We get our next equation there below, do a little bit more rearrangement, and we see that the half-life time is equal to 1 over K times the initial concentration. What's interesting about this is that the half-life concentration is dependent on the initial concentration for second order reactions. If we go back to the first order one, here we saw on the first order type of reaction that the half-life wasn't dependent upon the concentration. It was simply dependent upon the rate constant. It's different for second orders. Second orders, because reactions, we see from our equation here that it's dependent upon the rate constant, but it's also dependent upon what that initial concentration is that we're starting with. So that's a little different from first order versus second order. And like I said, the example that we work through is just a single reactant, that reactant is in second order. And the reason why we're going through that one is that's a little bit simpler calculation to do than it is when you have two first order reactants and then an overall second order reaction. Once in a while, you do get something that is a zero order reaction. And so a zero order reaction means that the concentrations of the reactants really don't matter, that the rate is the same. And the rate is essentially just the, it's just the reaction rate constant. So these are called zero order reactions. And in that case, we can plot that where here's our y equals mx plus b type of configuration, where y is the concentration at some time, minus k is the slope, time is what's plotted on the x-axis, and then the initial concentration, a sub 0, that's the y-intercept. And so plotted this way, they'll be linear. So once again, we saw that there was a certain way you could plot second order reactions to get a linear display of the data. There was a certain way you could plot first order reactions to get a linear display. And it's the same with zero order. You can plot them in this fashion and you'll get a linear plot. Okay, any questions about zero order, first order, second order? And like I said, the second order, just remember that what we're concerned with right now is even though you can have a second order reaction with a first order reactant, in other words, two first order reactants, we were focused just on an example where you have a second order reaction because you're second order with regards to one reactant. Any questions about any of the rate order stuff? What I'd like to do now is take a look at a couple example calculations. Here are some questions you can work on and you can do and go ahead and try for yourself, but wanted to go through a couple here just so everyone's clear on how to use the formulas. So the first one is 1431. And that question tells us we have this reaction, CH3Br methyl bromide, plus hydroxide to give us CH3OH, which is methanol, plus bromine anion. And so we're told that the rate law for this reaction is first order in CH3Br and first order with respect to OH minus. So this is an example here of where first order for each of the reactants, if those are both first order, then the overall reaction would be second order. And we're told that the concentration, if the concentration of methyl bromide is 5 × 10⁻³ molar, and the concentration of hydroxide is 0.050 molar, that the reaction rate at 298 K is 0.432 molar per second. So we've been given this information to set up the problem, and then now we need to calculate the rate constant. So remember, we said that the rate is equal to the rate constant times the molar concentrations of the reactants, and then the reactants are raised to whatever power each reactant's order is. So we were told the rate under these conditions is 0.432. Rate constant is what we're trying to find. And then the methyl bromide concentration is 5 × 10⁻³. Both of the reactants are first order, so we don't have any exponent on that concentration. It's just 1. And then the hydroxide concentration is 0.050. And once again, because it's first order, that exponent is 1 on that as well. So if we set it up correctly, then all it just is a matter of solving towards for K for our rate constant. And then our units, if we take a look at our units, we know that the rate is expressed as molarity per second. The two concentrations would be molar. So what we would find is, if we cancel our things out, we wind up with the units of this rate constant would need to be 1/molar seconds in order to cancel out on the right-hand side to get the units to match with molar per second there. So that's a case of writing out the units to kind of get comfortable with that would be good to make sure that you have things in the right units. We get some questions here about if the hydroxide is tripled, what happens to the rate? And so if we go back and look at our rate expression that we wrote out in part A, we see that if this was tripled, the 0.050 was instead 0.150, that the rate would triple. We see that in D, they ask if both of them were tripled. So if this 5 × 10⁻³ was increased by 3x and the 0.05 was increased by 3x. So that's a 3-fold increase there, 3-fold increase in the second one. So we'd have a 9-fold increase, a 9x increase in our rate. Because remember, the rate constant stays the same. The only reason that would change, only reason why that K value would change would be if we changed our temperature, and we're not saying we're changing the temperature. So the rate constant stays the same. The only thing that would be changing is those concentrations, and that would result in the increase in the rate of the reaction. Okay, let's look at 14.3.3. In this case, we're given a reaction of hypochlorite ion, OCl minus, plus iodine ion minus to give us OI minus plus Cl minus. And then we're given some concentrations of the two reactants, and then we're given the initial rates that were found for that. So let's just take a look at this information that we were given a little bit. So we talked earlier about one way to kind of figure things out is to hold things constant while you vary one of the concentrations. And we see the first two lines, we see an example of that. We see that the OCl minus concentration is varied. So it went from 1.5 times 10 to the minus third in that experiment. The next experiment, it was 3 times 10 to the minus 3. And the I minus was held constant at 1.5 times 10 to the minus 3 molar. So in that case, we doubled the OCl minus concentration, held the I minus constant, and what do we see? Our rate increased by a factor of 2. So that gives us some information with regards to the rate for OCl minus. We do the same thing, except now we're going to keep OCl minus constant. That's in experiment 1 and experiment 3. We varied I minus in 1 and 3, so 1.5 in experiment 1, 3.0 in experiment 3, and we see we get a doubling of rate constant there. So that's all pretty good information that we want. So since we see that we get a doubling of the concentration results in a doubling of the rate, we know that each of the reactants is first order. And so if we then write this out as each reactant being first order, we would get the rate equation of rate equals the rate constant times the OCl minus concentration times the I minus concentration. Since it's first order, the powers on each of those are 1. And so we know this because, kind of like the question we answered here, back here, when we said if both are tripled, the rate increased by 3. Whether if OH is tripled, it increases by 3. If they're both tripled, it increases by I. We see that direct relationship. And we saw that here. We saw doubling the concentration equal doubling the rate for each of those reactants. So that's how we knew that these were each first order reactants. Then the next part of the question, part B, is we're asked what are the units, and we're asked to calculate what that rate constant is. So if we go ahead and do that, we can simply take one of the rates that was in our table. In this case, I took the first one, this 1.36 times 10 to the minus 4th, and I took the concentrations for each of my reactants. Here it was 1.5 times 10 to the minus 3 for both. I took those and plugged those into my rate equation, and then I'm able to calculate out what K is, and it's 60 molar to the minus 1, seconds to the minus 1. And then finally, in part C, we're asked to calculate the rate when we now have the OCl minus concentration being 2 times 10 to the minus 3rd molar, and the I minus concentration 5 times 10 to the minus 4th molar. Well, I just calculated a rate constant in part B. So now I know that. And so if I can plug that into my rate equation, I can plug in my two concentrations that I was given. So now I have 60 times 2 times 10 to the minus 3 times 5 times 10 to the minus 4. Those are those concentrations. And then I can calculate the rate for those concentrations. Remember, I could use this rate constant because we didn't say anything about changing the temperature. All we did was change some concentrations of reactants. We'd already figured out what order those reactants were, and we had calculated in part B what the rate constant was for the reaction at this particular temperature. So we could plug all that information in and then calculate the rate. Okay, any questions about either of those homework problems? Okay, let's go on to 1441 then. In 1441, we're saying we have a decomposition reaction of SO2, Cl2 going to SO2 plus Cl2, and we're told that it's first order with respect to the SO2, Cl2. And at 600 degrees Kelvin, the half-life is 2.3 times 10 to the 5th seconds. So we're being asked, what is the rate constant at this temperature? So since it's a first order reaction, hopefully we remember that we use this formula. The half-life time equals 0.693 divided by Kelvin. So in other words, it's not temperature dependent. And so we simply just plug in our half-life time, our 2 times 10 to the minus 2.3 times 10 to the 5th seconds. And that equals the 0.693 divided by the rate constant. And then we can simply solve that equation to get a rate constant value. In part B, now we're at 320 degrees C, and it tells us that the rate constant at that temperature is 2.2 times 10 to the minus 5 seconds to the minus 1. So what we want to calculate in this problem, part of the problem, is what is the time, that half-life time. So once again, we use this formula, T1/2 equals 0.693 divided by K. We're told now that the K at this temperature, and notice they're different. This one's 2.2 times 10 to the minus 5. The other one was 3 times 10 to the minus 6. So different temperature, different K values. The 0.693 is part of that formula, and we used to do that math, and we get 3.2 times 10 to the 4th seconds as our half-life time. Okay? All right. Let's talk a little bit more about factors that affect reaction rate. So we have temperature. We've talked about that a little bit. There's also frequency of collisions and orientation of the molecules. So for a reaction to occur, the molecules have to run into each other. Okay, they have to interact with each other. And so they have to interact with each other, and depending upon what bonds you're trying to break or bonds you're trying to form, the molecules have to orient themselves so that that part of the molecule is interacting with the right part of the other molecule that you're reacting it with. So you've got to, first of all, you've got to have that collision, and second of all, you've got to have the right orientation. The final thing is that there's a certain amount of energy that's needed for reactions to take place. If you think about it, usually there's some type of bond breaking occurring. And we talked previously about how to break bonds in chemicals, you have to put energy in. And if it's not the right amount of energy, the bond breaking doesn't occur. So you got to get the right amount of energy in. So you got to have the collision, you got to have the orientation, you got to have the right amount of energy in there. Temperature factors in also, because temperature, you can think of that as helping increase the energy. The energy needed for the reaction to take place has a specific name, and that's called the activation energy. When we talk about the catalyst, we'll see how catalysts impact that activation energy. But the activation energy is really the amount of energy it takes to really make the whole reaction go. And it's usually tied back to some step in the reaction mechanism that's the most difficult one to accomplish. So let's first talk about temperature a little bit. We've hinted at this already, but in general, increasing the temperature increases rates. And so because the rate constant, because of this, the rate constant is temperature dependent. And just as the reaction increases as you increase temperature, the rate constant tends to go up as well as you increase temperature. In general, a rule of thumb is for about every 10 degrees C that you increase, the rate constant doubles. And over here on the lower right-hand side, you see a plot of temperature versus the rate constant, and you see it doubling as you have this 10 degree Celsius increase as you kind of go up. So you get this exponential type of increase in the rate with it. So, the reality is it's not as simple as just, oh, we'll just increase the temperature and keep increasing. And to really speed things up, there are limitations on that, which we won't go into in this class. If you take organic chemistry later, they'll get into that then. So I think for today, I'm going to end there, and we'll pick up on this on Thursday. Just to remind you again, Thursday we'll finish the kinetics chapter, and then next Tuesday, February 23rd, we'll have an exam on chapters 13 and 14. Any questions before we end? Okay, thank you.